Okay, so I guess let's start. So as you know, like this is the final week, and this week's material is about aspect-based sentiment analysis and all that. So most of the materials over there, whatever you have from the slides, that is good enough for the assignments and all. What I have planned is that last week I had done a basic outline or tutorial of sentiment analysis, so that was the a very basic model. So there is an upgraded part of that, so I was planning to discuss that. But since this is the last week, so we could also do something, as in, if you have any doubts regarding any of the other chapters which have been covered and all, anything general, not specific, but any general doubts if you have, then we can cover that a bit today. So otherwise I'll just go over this upgraded version of sentiment analysis.
I have one doubt regarding the performance analysis of any classification model.
Okay.
Like generally we calculate the precision, recall, accuracy, and F1 score for analyzing the classification model, right?
Yes.
But one of the assignment there is a very little bit specific, I think, to bootstrap method. I'm not remember exactly, but where they are asking about which actually parameter is good for our classification model. That means precision is sufficient or best suited for this, or recall is best suited for this, or F1 score or accuracy.
Okay.
So my doubt is that we are calculating these four. So ये हम लोग कैसे मालूम करेंगे कि which one is the more? मतलब यहाँ पे रिकॉल निकाल लेंगे तो प्रिसीजन निकालने की जरूरत नहीं है, यहाँ पे ऐसे प्रिसीजन निकाल लेंगे तो चल जाएगा, या फिर यहाँ पे F1 स्कोर निकालेंगे तो भी सफिशिएंट है, या एक्यूरेसी सफिशिएंट है.
Okay.
ये चीज मुझे थोड़ा कंफ्यूजन लगा क्योंकि उसका आंसर एक रिकॉल है एक्चुअली.
Okay, so the main thing is that so I'll speak in English for others also. So the main thing is that see, usually for any classification problem, accuracy is the most basic metric you can calculate to understand how they are doing. So accuracy is like how many are matching versus how many are not matching, that kind of thing. Okay. And precision, recall, and F1, they are more like sophisticated metrics. So precision is used for on a rough basis, you can think precision is out of all the things your model is predicting, how many is correct. Roughly, that is what precision means. Out of all the things model is predicting, how many is correct. And recall means out of the total correct things which are there in your data set, how many the model is able to predict. So this is the main difference between precision and recall. And as you know, F1 we can calculate using precision and recall. So the standard thing is that for classification problems, ideally you should be reporting the F1 is the most important metric, you can think. Normally F1 is the most important, but then there are some applications. Okay, so based on those applications, some other metrics may be more important than F1. Say for example, I'll tell you, see if you have say fingerprint detection. Okay, so fingerprint detection, that is also like a classification algorithm. So you are inputting your fingerprint, it will tell whether it is matching or not. Okay, so here for that kind of algorithm, it is very important that the precision is accurate. Okay, so what I mean by that is that if the precision is given priority, then what will happen is it may happen that somebody who has the fingerprint on the database, their fingerprint may not be recognized. Okay, he may have to try again like that. But the advantage is that there is no it won't be the case that someone who does not have the fingerprint in the database, his one is accepted. So you have to understand what the problem demands. So some kinds of problem, they demand that the precision should be higher, that is wrong things should not be predicted, that is more important. So like for example fingerprint or face detection, these kind of things. On the other hand, there are some applications where recall may be more important, where you are not bothered about the precision, rather you want that more things should be predicted. So for example, think of recommendations. So for one video there are say 5 more videos which are possible we can recommend. Okay, so the more you will recommend, then the user gets a chance to see what is exact, like the exact recommendation. So like depending on the application, like very specific applications, precision or recall may be more important, but in general classification problems, F1 is the most important metric. Like, could I make myself clear, more or less?
Yeah, but yeah, still some doubt. So I think it will clear when I do some classifications hands-on on that.
Okay, so you,
I understand fairly.
yeah, go on.
I understand your opinion on that.
Okay. Okay, so you have another look, then you will be able to get that cleared. Okay, so
Yeah,
yeah. So somebody asked forward backward algorithm with example. So are you talking about deep learning, or are you talking about that forward backward in like parsing, that one? Okay, so let me open the slide once. Yeah, so yeah, week 4, I get it. So this is about this thing, forward backward algorithms and Viterbi decoding, that one, right? Okay, so with example, uh, going over that with an example will be tough for me right now. So I think you can look at the lecture, because here there the professor has explained in very detail that forward backward thing. Because like even when I studied NLP, I used his slide to understand that part. So I think that one is pretty detailed over there. Okay, because if I go to discuss that, it will take a lot of time right now, and I also don't have anything prepared on that. So I can only tell you from the slides, but then I think it is better if you look at sir's lecture, because that is more detailed. He has explained the forward backward pass in detail. Yeah, but that is the point, right? You have to look at the videos like maybe multiple times to understand. Okay, so I can give a little bit of brief about that. With example, it is difficult, but I can walk over the algorithm from the slides once. That thing I can do right now. Okay, so I'll do that. Wait, I'll do that.
Hello, sir.
Yeah,
Sir, can you please also explain micro average precision and
macro
recall?
average. Okay, okay. I'll let me just cover his doubt first, then I'll go over that.
Okay.
And also somebody asked about sentiment analysis. I'll also discuss that briefly, don't worry. So let me just walk over this forward backward algorithm, because that is a bit tricky, I know. Wait. So let me share my screen. So this is the Baum-Welch algorithm. Okay, so what does this decoding mean? So like, as you know, these hidden Markov models, they are like just 1 second. Yeah, for exam pattern, I have no idea, because that is being said by the course TAs. So it is better if you ask them. We are not connected with that. Okay, so regarding this Baum-Welch algorithm, so the idea is that you have a transition matrix between states, and you have an emission like matrix, like for a given hidden state, what is the probability of emitting what. So I hope you understand the idea of like hidden state and emitted, like the observable state. So like in hidden Markov models, the idea is that there is a hidden state which you cannot observe, and from each hidden state there are some possible observations which you can see. So that is the emission. And when you see a change in the emission, that is because there is a change in the hidden state underneath, and like the only defined rules of changing are between the hidden states. So there cannot be any change between the emissions. Like you change from one hidden state to another, and from each hidden state you have different probabilities of emissions of different observations. Okay, so that is the basic idea. Now there are different ways of solving this thing. So I'll just walk over the slides once, if that is helpful. I'm not sure if it will be, but I'm just giving it a try. So like at any time you have a capital XT representing the hidden state. Okay, and YT is the observation state, observation variable. Okay, so like YT represents what you are observing, or the emission, and XT represents the hidden state which is underneath. Okay, and as you know, you will have a state transition matrix which is transitioning from one state to another. So that can be defined as a probability matrix, and there is an initial distribution of the hidden states. Okay, so when you are starting off, what is the probability of being in which hidden state, and finally the emission matrix is for a given state, what is the probability of emission. So to understand what these symbols mean, as you can understand, so X is representing the hidden state. So if X at t minus I is like t minus 1 is I, then what is the probability of X at t being J? That is how we define the state transition matrix. So row I column J of the matrix represents going from state I to state J, and this pi is a vector, and each element of that vector represents the probability of being in that corresponding state when you start the process. And this B, which is like a matrix defined over like the Y and X, so this represents what is the probability of seeing this observation YT when the hidden state is J. Okay, so this is what these things basically mean. Now you know, like we want to learn these things, or like given some real world data, we want to find out the value of these matrices. Okay, so we have to estimate them. Now in the data you have this sequence of observations. Okay, so y1 y2 up to yt, and the algorithm will try to find these parameters a, pi and b, like the state transition matrix, the initial distribution, and the emission matrix. That is what the machine learning model will try to learn. Okay, so you have the original data in the form of the observation of sequences. and the model will try to learn these parameters. All right. So the idea is, as it is being said here, that we start with some random initial conditions. So you assume the parameters to be something at the beginning. Okay, so you assume something, like that is how normally we do machine learning also. You initialize the models randomly and then you train it on the data, and those random values then change into something which makes sense for the model, right? So this is also what we do here. We start with random values of these parameters, and then we estimate the best values of state paths xt using these. Okay, so what does this thing mean? So let's see. So you choose some initial values for all these. So you have chosen, like you have set some random values to a, b and pi. Now you try to do a simulation. Okay, now you know that the main thing is that you try to like simulate this sequence of paths. Okay, and then you know what is the gold standard. So you have one example, say you have an example of y5, then y3, then y4, something like this. So then you actually started with taking different initial values for these parameters. So you start with some state. So let's say I'm calling the states with x and the observations with y. Okay, so you're checking all possible states, x1, x2, x3, how many states are there, you are checking that. And then you know that your original sequence is starting with say y5. Okay, so you check what is the probability of y5 from x1, y5 from x2, y5 from x3, and like that. So you get some values. Okay, then in the next step what you do is you try to see, had the first step been x1, like what is the probability that the next one is also x1 and I am emitting the what is there in the gold standard, say y2. So you have to try to mimic what is there in the gold standard and see how the values are coming up. Okay, and then this is how we actually do it. So we have this alpha I, this represents the probability of seeing up to this point. So you have a big sequence, as I said, so y5, y2, y4, suppose you have some more. So at any intermediate point we are considering, so this is how they formulate this. So you have the probability of seeing y1 to yt. So you have already done this part. This part is already done. So this is defined on recursion. I hope you understand, like recursion or mathematical induction, like that kind of principle this is following. So up to small t it is done. Now we are only going to show how we are going from small t to small t plus 1. So as they are said, you can find this recursively like this. So these are the two values that need to be calculated for you to update the parameters. Okay, so you when like at the very first point, like when the time is 1 at the very first instant, then the alpha I can be calculated by directly. So use alpha I means being at state I. Okay, so being at state I at time t. So what is the probability of being in state I at time 1? So that is, you multiply the probability of starting with state I and then you are emitting y1. So you have emitted y1, you can see this here, and then you recursively define this. Okay, so at t plus 1, what is the probability? So you are at this one, alpha it represents the current position, and you want to go to the next step. So that how you can do? So you are at state I at time t, you want to go to state j. Okay, like this is where you want to go, you want to go to j. Okay, so like you are taking possibilities of all states. So from all states you are making the transition to j. So that is why for all states the possibility of being at that state at time t and then making the transition from I to j. Okay, and you do this over all states, and then you multiply this with the emission probability of yt plus 1 from state j. Could you understand just this part? This is the forward part of the algorithm. So what this forward and backward means, that will come in a moment, but could you understand this, how we are formulating the problem? So we are saying that at time t we are at state I, and that is defined using this like this notation alpha I of t. That is the probability of going from all these states and then being at state t, going through all these observations, being at state t, state I at time t, and based on whatever parameters you have learned. Okay, so the initial condition is this, and the transitions are calculated like this. Now there is a backward way of doing it also. So as I said, at any point in the sequence, so you have a sequence of observations, right? y5, y2, y4, y3, like that. So at any given point you can look at the left side and see how I arrived here. That is this forward part. And then you can look at the right side and think, how will I get from this to the end? Okay, so that is how they define this backward part. So that is the probability of seeing all the things on the right hand side of the current position, t plus 1, t plus 2 up to capital T, given that the current state is I. So what is the probability that if I am at state I at time t, I will do all these transitions after this? Okay, so like ending the partial sequence, this one, the probability of the ending partial sequence, and this is the probability of the starting partial sequence. So at any given point you are seeing what is the probability of me getting here, seeing all those y1 to yt, and then you are seeing what is the probability of going to yt plus 1, yt plus 2 up to y capital T from where I am right now. So you are doing this at every point. So this is how they define this one as well. So probability of ending at time t is always 1. Okay, so because at time t the sequence has ended, so that is why the probability is 1 over there. And this part, sorry, and this part also comes from that. So you are calculating the probability of going to all possible states in the next point. So j is over all possible states, and you are seeing the, like, that will be then bj t plus 1, and you have made the transition from I to j, and at state j you are emitting yt plus 1. So this is how this is defined. If you see, there is a very like there is a symmetry between these two things, because one is defining from the left hand side and the other is defining from the right hand side. Okay, and then some more variables are being computed. This is pretty direct, like you are taking the possibility of starting the sequence as you have done and then ending, and you are calculating the, like, possibility that I is this state in this time t. Okay, so that is done by looking at both the left hand side and the right hand side. So as you would normally think, just looking at the left hand side does not help in learning the parameters. That is why we have to look at the right hand side also. So that is what they are saying, probability of being in state I at time t, given the observation capital Y, like this is the sequence of observations and the parameters. So that is defined like this. And this is another thing which they are defining as the possibility of being in state I at time t and state j at time t plus 1. So this is like probability of being at state I at time t, and this is you are defining a pair of states. Okay, so I at time t and j at time t plus 1, and that is defined using this, like if you just multiply those two together you will get this thing. So how will you update the parameters? Well, you have these two equations now, and then based on that you can calculate these things. Okay, so like this is expected number of times state I was seen at time 1. Okay, like you are doing a run over the entire data, right? So after you do these updates every time, so what you do is you make one pass over the data and then you change these parameters like pi, a and b, you change them. Okay, so we had started with some initial values randomly initialized, and we did those calculations based on that. So the first gold standard or the first data which you took for training, and you saw that, and based on that you calculated with those random parameters. Okay, now you got some values, right? You got these two values, like you have got these two functions after all these steps, right? Now you need to update your parameters just like any machine learning model. So you have to change the parameters. How do you do that? So that is why they say expected number of times state I was seen at time 1. So at time 1, expected number of times state I was seen, that will be defining pi I. And Aij is expected number of transitions from state I to state j compared to the total number of transitions away from state I. So like being at state I, what is the possibility that I will go to state j? That is, we are calculating from the data based on this formula. So like this is the formulation of it, this is what it means. Okay, so and then this is how you do with the other one also. So from a high level, I'll just walk over this thing once more so that it becomes clear. So we have these three parameters, A, B and pi. A represents the state transition matrix, B represents the emission matrix, and pi represents the probability at the like starting. What is the probability of being in which state when we start? Okay, so these are the parameters of your model and you have randomly initialized them. Then what you do is that you take one data which you have, like you have all these gold standard sequences of datas, as is being mentioned over here, that you have this part is given to you, like this is your data, you have this sequence of observations and you want to learn the hidden model. So you take the first sequence and then you calculate this alpha thing and this beta thing based on these two formulas. How they came I described briefly, but overall you have to calculate alpha and beta. Then you calculate this gamma and forgotten what this symbol is, but whatever this is, like this one. Okay, so you calculate these two variables as well. All right, so you took those random values which you have initialized with. Based on those values you are calculating this alpha, beta, gamma and this thing. You have calculated all of them, and then based on whatever you have calculated, you will now update the parameters which you have. So this is how the machine learning part works. Could you understand anything at like even briefly what is happening, if not in details?
Yeah.
Okay, no, like the one who asked the question. Yeah, like even if you have understood 50%, I'm happy with that, because it's difficult to do more than that right now. You have a look in a bit more detail. The overall idea is this: we are calculating these alphas and betas, and then we calculate gamma and delta, and then we update the existing parameters based on whatever we have calculated. And how those formulas are making sense, for that you'll have to just go over the things a few more times, then I guess it will be a bit more clear.
I
Okay.
think yes, on okay, please carry on, finish it, and then maybe I'll ask.
Okay, so you can put whatever question you have in the chat box, because there are some more pending questions, so I'll answer them first. So
Okay. No, I mean, there's no specific question from mine. I just the week 4 sessions were a bit hectic and tricky. If I remember, there were a lot of things that talked about,
yes.
especially Baum-Welch algorithms and then maximum entropy models. So
Mhm.
those were a bit tricky and difficult to grasp. So if possible, maybe quick overview would be very helpful. That was my request.
So I gave the overview of bomb welch right now. I'll see if I get time to do an overview of the other things also. But as far as I remember, this is the most trickiest one among all of them. The others are a bit more straightforward. Okay, I'm seeing. So let me just look at the questions asked by others once. Okay, so yeah. So let's look at the next question. So somebody asked how to go about the NLP project on sentiment analysis. Okay, so this NLP project on sentiment analysis, like you want to do some project with real world data, or you want to learn about sentiment analysis? Like, do you want a tutorial kind of thing, or do you like want to do a real project? Like even if you want to do a real project, you will have to look at the tutorials, right? So um, real world data. So that is the, like, you have to get some data based on what you want to do. Like there are many data sets which are available. Regarding understanding what to do, like the session I gave last day, that was a brief introduction into sentiment analysis, and it used real world data set. Okay, so you can have a look at that series. I'm just pointing that out. So there is a series of tutorials. Yeah, so I'm giving this thing in the chat over here. So there is a series of tutorials on sentiment analysis. Okay, so you can look at it. So they cover step by step. So the part one of this thing I covered the last day, and then the next parts they build on part one and they go forward. Okay, so but this is based on PyTorch and they use deep learning for this. So I guess this is a good starting point for a like serious project on sentiment analysis. So you can start with this. Okay, and they have really detailed the notebooks, so it's like makes it easier to understand. All right. um Forward backward is done, this is done. Okay. Somebody asked me about uh like macro and micro precision or something, like there was some question like that somebody had asked. Okay, so the main thing over here is, so suppose you have like, as you know, in classification problems there are some categories. So like the basic category is known as binary classification. So you have a data, you just have to say positive or negative or 1 or 0. So that is binary classification. Then you have something known as multi-class classification. Okay, so multi-class classification means, say, given an image of a animal, say which type of animal it is. So there are 4 or 5 categories or maybe more. So these are multi-class classification. Okay, and there is something more which is known as multi-label classification, where like more than one class may be relevant for a given example. Okay, but let's consider the example of multi-class classification. So if you think of multi-class, you may have multiple classes, as I said. So imagine that you have a data set of animals and you want to try to predict which category of, like, maybe mammal or bird or reptile, something like this. These are the classes, say. I'm just giving an example. Now you think that suppose in your test data, suppose there are 5 classes and all those 5 classes are equally distributed, like 20% each to each class. So like there are like same number of examples belonging to each class, right? So if you think that, then in that situation, micro and macro are the same thing. I'll explain what micro and macro mean exactly. But in where you have the data to be fully balanced, like the classes are fully balanced, then micro and macro will give you the same values. But if they are unbalanced, what happens then? So macro is macro average says that we calculate the metric, like whatever you are doing, precision or recall or F1, whatever you are doing, we calculate that for each class individually. So individually each class, you see, you calculate the precision and the recall, whatever you want to calculate individually for each class you do, and then you average all of them together. So what this does is, even if your data is not balanced, say there are 5 classes but there is one class which is just having 5% examples and some other class is having maybe 30% examples, you can have, like, real world data will not always be balanced, right? So then Macro, what it does is it assumes that when you are measuring the final performance, each class is equally important to you. So the number of examples per class is not important. Each class is important on its own. Okay, so then what you are doing, you are calculating the metric for each class and then you are averaging them. So this assumes that every class has equal weightage, right? So that would mean if your model is not doing well on that 5% class, like the class which has only 5% examples, the rare class, if your model is not doing well on the rare class, it will be penalized, because the rare class has 5% examples but it will contribute 20% to the final metric. So that is the idea. Macro is basically we calculate for each class and then we average, so that all the classes are represent fairly when we do the evaluation, when we calculate the final metric. Micro, on the other hand, disregards the class imbalance and it rather focuses on the number of examples. So you take total, like you don't do per class basis. You look at the entire data set and you calculate on a whole. Okay, so that is micro. So for micro, you don't do it class wise. You take the entire data and do on that thing normally itself. Okay. So what that would mean is that the class which has more examples, that will be evaluated more times, and the class which has less examples, that will be evaluated less times. Okay, so that will come into the picture. That is why whenever you see any real world, like if you see any papers and all who have reported both macro and micro metrics, you will see that the micro is always higher. Micro is always higher because micro disregards the imbalance and it places importance only on the number of examples. Now in general, all machine learning models tend to learn the class which is more frequent. The model tends to understand that better, and the classes which are rare, that is more difficult for the model to understand. So that is why if you do micro, you will always see that the class which has more examples will get more contribution in the final score. So that is why you will have a higher score. And when you do macro, the low performance on the rare class will penalize. Okay.
Okay, sir. So, in what situation we should use this macro average?
Ideally, you should always report macro. Like micro, you can report it additionally, but you should always at least report the macro, because macro actually assumes that all classes are equally important. Does not matter how many examples are there, right?
Okay, okay.
But I think the point is see these are the statistics that we capture after our to check our performance of the model. So if there is an imbalance, ultimately, I mean, this can only tell us, will this actually tell us there is an imbalance in your data? Or let's say if the precision or recall is not so good, this will not help us to understand that the reason for this was any kind of disbalance. Right? That we as a part of training the data model itself, before we have to
Yeah.
make sure that we don't have unbalanced or imbalanced data, right? And then accordingly we
That
have to
is
set parameters.
that is not always possible. Like you will often have real world data that is, leave alone being balanced, that has a long tail distribution, say. So there are some classes which are very frequent and every other class is very rare. There is no way to balance that. Okay, so there people do other things for trying to make up that lack of examples. But when you calculate the performance, that is when you should always do macro, so that all the classes which you have considered, they get equal importance in the evaluation. So suppose like the model which does better on the rare class is generally considered a better model, generally, like not always but generally. So that is why if you do the macro, then you will see models which are doing better on the rare classes will get higher scores.
Okay.
Now that generally doesn't happen, that a model is doing specifically well on the rare classes and poorly on the frequent classes. That usually does not happen. It's a very abnormal situation. Like people always think of how do we capture or reflect the rare classes when the data is imbalanced. So that is why macro is always preferred. Now then people sometimes, as I said, the micro value is always higher. So sometimes people don't want to show a lesser value, they want to show an inflated value or something. So that is why they report the micro. But that is not scientific per se. You should always report the macro.
But any thoughts on or practices that you would recommend to overcome? Yes, as you said, most of the time in real world data you get unbalanced data, but that if you train with that unbalanced data, you may, as you talked about, right, the model tends to give more weightage to higher classes, and the predictions is not very good for the low for the class which has low amount of data. So hyperparameter tuning is one way of maybe.
One of the
Yeah.
easiest tricks, like there are a lot of techniques, like this is actually like ongoing research problem, like how do you mitigate the rare classes.
Yeah.
But one of the like easiest tricks or techniques you can think is that you have something called a weighted loss function. Okay, so
Yeah.
when you are calculating the loss, that time you give different weights to different classes, and
Yes.
basically the classes which are rare, you give them more weights. So if the model makes a mistake on a rare class, then the model is penalized much more heavily. Okay,
Yeah,
so
I
the
had
model
one
learns.
specific question for this. So I was recently training a logistic regression model for this. So now when you say, so let's say I had two classes, a binary classification 0 and 1. So let's say if I give a weight of higher weightage to a 0 or any class, let's say 0. So what exactly happens? What are the consequences? I mean, we say I understand that you give more. I mean, if there is you give higher weightage, so means is higher correction or higher punishing has been done to that whenever an error is detected. So what is the meaning of this exactly? What happens? I mean, what is the
It
impact of
kind
this on
of,
the overall?
so kind of, it's like you can think like this is not what is happening, you can think of it like this. Say as you said 0 and 1,
Yeah.
suppose the one class is three times more, like there are three times more examples for the one class than the zero class, suppose. Okay, and then say you set the loss weights as 3 is to 1. So for the zero class the weight is three times the weight of the one class. What
Yeah.
this means is that when you see one example, so and suppose your model is making a mistake every time, suppose.
Yeah.
So
Yeah.
then when you see a zero class, you make an update which is equal to three times what you would update when you make a mistake on the one class.
Okay. So
So
what I mean, so this
so that
leads to
that
better
kind of
detection.
that kind of mimics, I'm not saying exactly, that kind of mimics what would have happened had you actually had like equal distribution among the classes.
So what exactly I did was it was not a really imbalance. I had a balance set, but even though I had a balance set, I did a hyperparameter tuning and I got the results which did not give exact equal weightage. I mean, I understand why it was that. So what my idea was, let's say if I give a higher weightage to one of the class, and so there is higher punishments to that class whenever an error is made. So can I assume, or can I, let's say, understand that when let's say I give a higher weightage to class 0, so whenever the model is predicting class 0, uh, maybe the prediction of class 1 may not be very accurate, but prediction of class 0, the model can be something like this. It says, okay, if it is 0, I'm more accurate about being it 0 than I'm accurate about being it 1. Can this happen if I do this in a
Yeah,
balanced set?
like you can, there is a possibility of overcorrection, like you,
Uh,
like that is something which you'll have to look at the performance and then change the weights. So the
yeah.
weights you assign to individual class, that also becomes a new hyperparameter, right?
Yeah,
So
I mean,
that
I
you'll
saw
have,
that behavior. I saw that behavior that whenever it was giving a 0 prediction, that was the recall and the precision and accuracy of that class is very high. It was false positive very less. I mean, it was able to detect false or true negatives much more efficiently, much more better than becoming it. So that was something that I saw while tuning this hyperparameter. Okay. All right.
okay.
And when we are going to the exams, there are a lot of formulas, Sonak. So are we supposed to, memorize all of them, or will that be any kind of help that would be given? I mean,
So,
because lot of formulas to.
yeah, you can think that the basic formulas, like say
Hmm.
calculating some metrics, like say PMI or things like that,
Hmm.
those you'll have to remember.
Hmm.
But the
Okay.
bigger formulas or like things which are complex, there you can think like if either those things won't be given like in a way where you have to remember the formulas, or
Hmm.
it will be given in a way where some information will be given to you. so that you
Okay.
can, or maybe the formula also might be given, you have to do some kind of calculation or something, so that can also.
Okay, that's good to know, comforting to know. Uh, all right.
Okay, so somebody had asked about a practical tutorial on NLP for beginners. Now, this is a difficult thing to answer. Like, practical tutorial on NLP, as in for beginners, see, whatever has been discussed in this course is kind of, you can think what you will, like if you try to implement those things, that will be something you do as a beginner, because these days like these all the things which you are learning, most of those were devised in the earlier days when people used to make features and build all these things on their own. Right now, NLP, everywhere you have deep learning coming into it, right? So if you think of that from that point of view, then like if you want to understand the basic things, you can just Google them. Like say, like what should I give as an example? So say a CRF. Okay, so CRF implementation or things like that, you can see how they are doing. But then if you actually want to do serious NLP, and like from a beginner's point of view you want to get into that, then I think it's less about NLP and more about deep learning. So then it becomes more about a practical tutorial on deep learning. So you'll have to understand how deep learning works. If you understand that, then NLP component of deep learning is not that much, if you understand how deep learning works. So that is how I can say, like if you are looking for practical tutorial for absolute beginners, then there are these two categories. One is the traditional methods, those if you Google them directly you will get, and if you don't get, that means that is pretty rare, people don't do it anymore or something like that. But the common things you will get, like you will get materials. And if you are talking about doing it from the deep learning point of view, then it's better to actually look at deep learning tutorials. So like if you are doing with PyTorch, you can look at the PyTorch website. Then there are a lot of related blogs and posts on Medium or towards data science. So if you Google them, like the exact thing you want, then you will more or less see in the first page of Google search there is a article from towards data science on that. Say if you just Google sentiment analysis using PyTorch, you will get one or two tutorials on towards data science also. So those are the sources more or less you can look at for beginners, because as a beginner you need to understand what component what is doing. So these kind of things, they give detailed explanations, and also it becomes easier to understand. Polarity shift. What is polarity shift?
It's one of the mechanism to mitigate the problem of the negation problem in sentiment analysis. So whenever you have encounter negations, how do you deal with the polarity of the adjective or the words with the negation?
Okay, I actually did not look into the material this week because I had prepared something else. So maybe I'll have to look into that to answer, or like
So
maybe
basically,
Abhishek actually
yeah.
gave the answer. So
Yeah, so basically, if the let's say polarity of a word, let's say terrible is -3, and we say not terrible. So what would be the polarity when a negation is applied? So one of the techniques to handle this was a polarity shift, wherein you simply do not reverse. Let's say if it is terrible is -3, not terrible becomes +3. We don't directly reverse it, but we add some polarity value to come to some common ground. Now, the only question I also have is what is the number that we had? How do we decide to the number? That was actually not covered, and I will also not researched a bit about it right now. But the idea towards is that we don't directly we have a mechanism of function that we apply which does not completely reverses but mitigates by adding or reducing the polarity when negation happens.
yeah, I actually did not look into that this week that much. So maybe I'll, like if you have a more detailed question, perform normalization. Uh,
No, not normalization. Normalization was a different thing. If you see the sessions that were covered in the last one, it was not that. So normalization was a different thing altogether. Let me put it this way.
Okay. So, do you have any other questions from the previous chapters? Anybody?
I had noted couple of things that I'm not getting it right now. Yeah, one thing in the I think week 2 when we were talking about some of the common applications when NLP were edit distance and stuff.
Hmm.
So there was while calculating edit distance, we had different varieties of it was a edit distance normal, then weighted, and then there was something called symmetric delete spelling correction. I actually did not understand this particular concept. If you can talk
So
about it.
it's in the lecture, right?
Yeah. So week 2 lecture 6 or 7 maybe. Yeah.
So towards the end. Tell
Yeah. So when we talk about weighted edit distance, it's after that, I guess. Before language models, yes. Yeah, other variations of weighted edit distance. So we talked about transpose, and then there was something as symmetric delete spelling correction.
Wait. So weighted basically means that you are giving different weights to these things. Like
Yeah.
depending on what you are like which character you are adding or which character you are deleting or which pair you are making the substitution between, there will be different weights based on that, and these weights have been learned from some real data or something like that.
Yeah.
This is
Not
what.
this. After that we have there will be. Yeah, go down. Then there is one topic called symmetric delete spelling correction. That was something. This was for transpose that you're seeing right now.
Yeah.
Transposition was fine. I'm not sure if you find this. Yeah, this one symmetric spelling correction. I did not actually get this. What was the idea behind this? What was it exactly? What problem was it solving and stuff?
Okay, so let's just back up a bit and see what they're telling. So how do you find dictionary entries with smallest edit distance? So they are saying generate all possible terms with an edit distance of less than equal to 2. Okay, so all from all the operations and search them in the query. For a word of length 9, this will lead to so many terms which you are searching for. So, and for Chinese this becomes much larger. So the idea is, so you generate terms with an edit distance from each dictionary from the input terms. Okay, so like for like they're, I think what they're trying to say over here is that in the dictionary itself you maintain for each word what is at edit distance of 2 from that word. Okay, and then from the input which you are getting, so this is offline, this is done beforehand, right? And then from the input you also find for every word the input those words which are less than equal to 2 from that. And then after that if you do the computation, then I think what they're trying to say is over here the number of computations becomes very large, so that will get reduced by a great degree, because over there also you have done some kind of edit distance, like you have calculated the edit distance less than 2 from that, so then it becomes easier to search instead of trying to see what I can get just from the query. So they are also taking for each term in the dictionary, they are keeping those terms which are at 2 length from that. Okay,
All right.
so as you can see, then the number of deletes within edit distance less than equal to 2 for a word of length 9 will be 45. Previously it was much larger. Okay, so because you have shortened it on both sides, but then you have to check to remove the false positives. Like some will match falsely because you're also taking the shortened part from the dictionary, right? So some can match falsely, so you'll have to do a further check on that. All right.
So you're saying, I mean, the dictionary itself stores what are the possible
Yes. For every
edit.
term, it also stores the other terms which are like edit distance less than equal to 2 from that one. So like a kind of mapping you can think, or it stores them directly. However, you think like there is some kind of thing being stored. So like you are generating them from each dictionary term, and this is done offline. Like so, it is done beforehand, and online is the part which you are doing when you are putting in a query or something. Okay, like when you are putting in the input.
So that term, so when we are giving an input, so we said it's like generate terms with edit distance 2 from the input. So generating those terms will still be very expensive, right? I mean, let's say, as we were seeing in the above things, so let's say it mentioned, right? Generate all possible terms with edit distance 2. So for our, this will still be valid, right? For in online mode.
No, you are looking at deletion from both sides. That is why.
Okay, okay.
Here, what we were doing previously is you are checking all, you are generating all possible terms with an edit distance of less than equal to 2 with all operations. But here they are saying you do with like less than equal to 2 edit distance deletion only, both from the dictionary side and from the query side. So then you match the shortened, like the deleted
Oh,
version of the terms, and
okay.
then you need to later do a, that is why you need to later do this further check to remove the false positives, because some will match because the shortened versions are equal but not the words are same. Okay,
Okay, okay, got it. So basically,
this is
okay, you're
removing
shortening it and matching it.
this
That's
is removing all other operations, just focusing on deletion.
okay. Got it. Got it.
Okay, so I guess that's it. um, any other doubts?
Not much as of now. In the bigram models and trigram models, when we are considering those, the beginning of the sentences and the end of the sentences, these needs by default we consider them until specifically mentioned, right?
Just one second. Yeah, go on once more. What you were saying?
Yeah. So when we're talking about bigrams and trigrams and other stuff, right? So the beginning of the sentence, like the sentence beginning and the end of the sentences, those also should be considered
Yes,
while calculating this,
yes,
because
like the start of sentence symbol and the ending sentence
yeah.
symbol, that thing. Yeah. Like even if it is not mentioned explicitly, you will think that it is there because otherwise you won't be able to do those calculations.
Okay.
Any more questions?
Yep.
So,
Thank you.
okay, thank you everyone then. I hope these sessions were helpful, at least to some degree, to all of you. And
Will Will you be able to take any more sessions? Maybe next week, last or this is the last one?
no, this is the last one. So even we have other things on next week. So
Okay. Okay. Thank you. Thank you very much.
thank you everyone.
And Sonak, I had sent you one mail. I was waiting for a reply. There was a query. If you, there was few questions from assignment 7, I guess they were regarding which I had sent you.
Yes, I think you were told one day, so I had waited a few days, but then I did not see. So I did not check after that maybe. So if you could just once more, like,
Okay. Do you have your maybe email ID again? Maybe I maybe must have copied the wrong email ID. Maybe I don't know. So give me it again, and I'll send it to you. Okay. Thank you. I'll send it again.
okay, thank you
Thank you
everyone.
so much, Sonak. Thank you for your time. Yeah.
Thank you.